Welcome back to the Deep Dive. Today, we are absolutely cracking open a paper that didn't just, nudge things forward. It fundamentally reshaped how computers see the world.
Mm-hmm.
We're diving into ImageNet classification with deep convolutional neural networks, a pivotal work from way back in 2012 by Krizhevsky, Ilya Sutskever, and Jeffrey Hinton.
Yeah, and this wasn't just a paper. It really felt like the moment that demonstrated the incredible power of deep learning for a really complex real-world problem.
Right.
So our mission here is to unpack the key insights, the really crucial bits, and the specific innovations in that paper that led to this, paradigm-shifting breakthrough in image recognition.
And it's so important to set the scene, right? The context of the time. Because before 2012, the dominant thinking in computer vision was that you had to be really clever yourself.
Right.
You had to hand engineer features based on how we understand vision. You told the computer exactly what to look for.
That was totally the standard approach. You'd build these complex pipelines, hand-designed steps to find corners, edges, textures, stuff you, the human expert, decided was important. In fact, they even mentioned this anecdote in the intro. Apparently a similar paper, one using neural networks for vision, got rejected years before by a top conference.
No way.
Yeah, because the reviewers felt it gave no insight into how to design a vision system. That just shows you how skeptical people were about learning approaches for this stuff.
Wow. Rejected for using neural networks.
Yeah.
That really says something about the mindset then. But these authors, Krizhevsky and team, they had a different take.
They really did. Their argument was basically, look, for really complex tasks, like recognizing objects in messy photos where there's tons of variation and noise, learning the features directly from the data is ultimately going to beat hand engineering if you have enough computing power and, crucially, enough data.
And that data part, that was a huge roadblock for ages, wasn't it?
Oh, absolutely critical. Before this, the data sets people used were, tiny compared to now. Tens of thousands of images, maybe.
Like MNIST, CFAR.
Exactly. Fine for smaller tests, but just nowhere near enough to capture the crazy variability of real-world objects, different lighting, poses, backgrounds, you name it. You need way more examples for that.
Which brings us to ImageNet.
ImageNet, yeah, that was the absolute game changer for data, led by Fei Li and others. It's huge. The full thing is over 15 million labeled high-res images, like 22,000 categories.
Wow.
But the part they used for the competition, ILS-VRC, that was key. 1.2 million training images across 1,000 categories, plus validation and test sets.
What?
That scale was just unprecedented. And it finally made it possible to train these really big models powerful enough to learn from that complexity.
Okay, so ImageNet solves the data problem. What about the model itself? You mentioned convolutional neural networks, CNNs. They weren't brand new then, were they?
No, not at all. CNNs had been around since, the late 80s. Jan LeCun and others pioneered them. They have properties that just make sense for images, right?
Like what?
Well, they assume useful patterns repeat across an image that's stationarity, and that nearby pixels matter most locality.
Okay.
This structure means they need way fewer parameters than a standard, fully connected network of similar size. So, in theory, they should be easier to train.
Yeah, there was a but.
Yeah.
Applying them to something like ImageNet with those high-resolution images was still a massive computational hurdle.
Exactly. Training a CNN big enough and deep enough for ImageNet was just too computationally expensive until graphics processing units, GPUs, became powerful and programmable enough.
Ah, the hardware catching up.
Yeah, so this paper really hit this perfect moment. The right kind of data, the right model architecture, and finally, the compute power becoming available.
Okay, let's get into their solution then, the network itself. They called it supervision. What did it look like? How big was it?
It was a beast for 2012. 60 million parameters, 650,000 neurons. Structurally, it had 8 learned layers, 5 convolutional layers doing the initial feature crunching, followed by 3 fully connected layers doing more abstract reasoning, and then a final 1,000-way softmax layer to pick the category.
And how do they handle the input images, since ImageNet picks aren't all the same size?
Good point. They standardize things. First, downsample everything to 256 by 256 pixels. Then, for training, they didn't even use the whole image. They took random 224 by 224 patches from those images.
Random patches, why?
And their horizontal reflections, too. It was actually a clever way to fight overfitting, which we'll talk more about. It basically creates way more training variety from the same base images.
Ah, okay. Data augmentation. Got it.
Yeah.
So besides the overall structure, what were the specific tricks or innovations they used that made this thing work so well?
Right, there were several key things. One of the biggest, maybe simplest sounding now, was using rectified linear units ReLUs for their activation function.
Instead of the old tan or sigmoid.
Exactly. ReLUs are just max 0x. If the input's positive, it passes through. If negative, it's 0.
And why was that simple change so important?
Because ReLUs don't saturate. Tan and sigmoid flatten out for large inputs, right? Their gradients become tiny.
The vanishing gradient problem.
Precisely. In deep networks, multiplying those tiny gradients layer after layer makes training incredibly slow, or just stall completely. ReLUs don't have that problem for positive inputs. The gradient is just 1.
Or 0, yeah.
And the effect was dramatic. They showed a plot. Their deep CNN with ReLUs hit a 25% training error 6 times faster than the same network using TARN. 6 times.
That's huge when training takes days.
It basically made training networks this deep practical within a reasonable time frame. It wasn't just a speed up, it was an enabler.
Okay, ReLUs were key.
Right.
What else? You mentioned the network was huge, 60 million parameters.
Yeah.
Did that cause hardware issues?
It did. The GPUs they used, NVIDIA GTX 580s, only had 3 GB of memory each. The full network was just too big to fit onto one GPU.
So they had to split it.
Yep. They worked out a scheme to run it across 2 GPUs. Basically split the neurons and kernels roughly in half.
How did they manage the communication between the GPUs?
They were clever about it. Communication only happened in specific layers, not all of them. This let them train a model roughly twice as big as a single GPU could handle.
And did that bigger size actually help performance?
It sure did. Using 2 GPUs let them build that bigger net, and it lowered their error rates, top 1 by 1.7%, top 5 by 1.2% compared to a half-size network on one GPU. And it trained slightly faster, too. Just showed that scale mattered.
Okay, so more compute meant better results. They also used some kind of special normalization layer, didn't they?
They did, yeah. Local response normalization, or LRN, applied after ReLU in some layers.
What was the idea behind that?
It was kind of inspired by lateral inhibition in real neurons, basically creating competition between neuron outputs that are in the same location but respond to different features.
Making features stand out more.
Sort of. It helped with generalization, gave them another boost, reduced top 1 error by 1.4%, top 5 by 1.2%. They did note it was maybe better called brightness normalization, though.
Interesting. And even pooling. They tweaked that too.
Just a subtle tweak, but yeah, they used overlapping pooling. Standard pooling looks at non-overlapping patches, right? Like a 2x2 window moved by 2 pixels. They used a 3x3 window, but still moved it by 2 pixels, so the windows overlap slightly.
And that small change made a difference.
A small one, but consistently positive. Dropped error rates by about 0.4% and 0.3%. They also felt it made the model a bit more robust against overfitting. Every little bit helped.
So piecing it together, you've got stacks of convolutions, ReLUs, this LRN stuff, overlapping pooling, then the fully connected layers also with ReLUs, and finally the softmax output.
That's the basic flow. And they really stressed the depth part. They tried removing any single convolutional layer, and performance dropped noticeably, like 2% on top 1 accuracy.
So the hierarchy of features learned across layers was crucial.
Absolutely. It wasn't just about having lots of parameters. The depth itself was key.
Okay, but still, 60 million parameters, even with 1.2 million images from ImageNet. That sounds like a recipe for overfitting, where it just memorizes the training data. How did they stop that?
Yeah, overfitting was a massive concern. They relied heavily on 2 main strategies, both now standard practice. First, data augmentation.
Right. You mentioned the random patches and reflections. That was part of
the
it.
first big part of it. Generating those translations and reflections by randomly cropping 224 by 224 patches from the 256 by 256 images. That effectively increased their training set size by a factor of like 2048.
Whoa.
And they said it was absolutely critical. Without it, they had huge overfitting problems and would have had to use much smaller networks. They also did this on the CPU while the GPUs were training, so it was almost free computationally.
And they used a similar idea at test time, too.
Right. For a test image, they take 10 patches, corners, center, and their reflections run all 10 through the net and average the predictions. Gives a more robust result.
Smart. What was the second type of augmentation?
It involved messing with the colors, specifically altering the intensities of the RGB channels based on a principal component analysis, a PCA, of the pixel values across the whole ImageNet dataset.
What does that achieve? Sounds complicated.
The idea is to make the network less sensitive to changes in lighting conditions and overall color balance in the image. Real-world lighting varies a lot, right?
Yeah.
This technique captured that kind of invariance, and it helped to reduce the top one error by over 1%.
Okay, so massive data augmentation. What was the other main weapon against overfitting?
Dropout. This was pretty new and radical back then.
Ah, yes.
Ah,
Where you just randomly turn off neurons during training.
exactly. During each training step, for each training example, every neuron in the hidden layers had a 50% chance of just being temporarily switched off its output set to 0.
That sounds crazy, like randomly firing half your staff every day. How does that possibly help?
It sounds nuts, but it's brilliant. It prevents neurons from becoming too dependent on each other, from developing these complex co-adaptations that only work for the training data.
Ah,
If a neuron knows its neighbors might randomly disappear, it has to learn features that are useful on their own or useful in combination with lots of different random subsets of other neurons. Makes everything more robust.
it worked.
Very effectively. They said it roughly doubled the number of training iterations needed to converge, but it was crucial for fighting overfitting. They used it in the first 2 fully connected layers.
And at test time, you don't drop neurons then, do you?
No, at test time, you use all the neurons, but you scale their outputs down, in their case, multiplying by 0.5 to account for the fact that more neurons are active than during training. It's an approximation that works well.
Okay, so we have this powerful mix. Huge network, massive data set, GPUs, ReLUs for speed, multi-GPU for scale, LRN and pooling tweaks, plus heavy data augmentation and dropout for regularization. How did it all perform on the actual ImageNet challenge?
The results were, well, stunning. Just absolutely dramatic. On the older ILS-VRC 2010 test set, where labels were public, their network got a top 1 error of 37.5% and a top 5 error of 17.0%.
Put that in context, what was the state of the art before them?
It wasn't even close. The previous best on that 2010 set used things like sparse coding and got like 47% top 1, 28% top 5 errors.
So they went from 28% down to 17% on top 5.
Exactly. Almost halved the top 5 error compared to the best traditional methods from just a couple of years earlier. It was a massive, massive leap.
Unbelievable. And they entered the actual 2012 competition with this, right? The ILS-VRC 2012.
They did, and they just blew everyone away. They won with a top 5 test error rate of 15.3%.
15.3, and the runner-up?
The next best entry, using more traditional computer vision techniques, was way behind at 26.2%. They also showed you could push the score even lower by averaging predictions from a few similar networks.
Ensemble methods.
Right. Averaging 5 CNNs got them from 18.2% down to 16.4%. And then pre-training on a slightly larger ImageNet dataset and averaging 7 CNNs got them to that final winning 10.3%.
Amazing numbers. But beyond just the scores, did the paper give any insights into what the network was actually learning? Could they, look inside?
They did try to visualize things. Looking at the filters learned by the very first convolutional layer, they saw stuff you might expect, filters sensitive to edges, orientations, different frequencies.
Like basic visual building blocks.
Yeah, but also filters that responded to specific colors, like colored blobs. And interestingly, because of their 2 GPU setup, they noticed some specialization. One GPU tended to learn more color-agnostic filters, the other more color-specific ones.
Huh. The architecture influenced the learning.
Yeah.
That's cool. What about higher-level understanding? Did it learn about similarity?
They explored that too. They took the output of the last hidden layer, this big 49T6 dimensional vector of numbers, as a kind of feature signature for an image.
Yeah.
Then they looked at which training images had feature signatures that were closest in simple Euclidean distance to the signature of a given test image.
And what did they find?
They found the images retrieved were often semantically very similar, even if they looked quite different at the pixel level. So you'd put in a picture of a dog, and it would pull out other dogs in totally different poses or breeds. Or different elephants, different angles.
So it wasn't just matching textures or colors. It had learned a more abstract concept of dogness or elephantness.
Exactly. It was compelling evidence that the network was learning meaningful, high-level representations of objects, representations robust to visual variations. That was huge.
So zooming back out, the depth was critical. They confirmed that.
Yep. Removing layers hurt performance significantly. The hierarchy mattered.
And when they wrote this in 2012, what did they see as the next steps? How could things get even better?
Well, they mainly pointed to basically waiting for faster GPUs and even bigger data sets, just scaling things up further. They also mentioned unsupervised pre-training as a possibility, though they hadn't used it here.
And the paper mentions the impressive response from the field afterwards.
Yeah, that's putting it mildly. It was more like a seismic shift. The computer vision community, which had been so focused on hand engineering, just pivoted incredibly rapidly towards deep learning, almost overnight.
And the rest is history, as they say.
Pretty much. Google, Facebook, Microsoft, Baidu, everyone jumped on board. We saw incredibly rapid progress after 2012. Better hardware, much deeper networks, building on these ideas, new techniques. Error rates on ImageNet plummeted, reaching superhuman levels on static image recognition within just a few years, around 2015.
It's incredible. And while Krizhevsky, Sutskever, and Hinton deserve enormous credit for the network and the training, they were also clear about the importance of the data itself.
Absolutely. They gave huge credit to the creators of ImageNet. That massive labeled data set was the essential fuel. You needed the algorithms, you needed the GPUs, but you needed that scale of data to make it all work. It was really a perfect storm.
So to wrap this deep dive up, this 2012 paper was just monumental. It showed the incredible power you could unlock by combining these large, deep CNNs with massive data sets and powerful GPUs.
It just shattered the previous limits in image recognition and really ignited the whole deep learning revolution we're still living through, proved the concept on a massive scale.
And this wasn't just some academic paper, right? This is the work that directly led to so many applications you encounter constantly, how your phone sorts photos, the systems in self-driving cars. It fundamentally changed how we get computers to perceive the world.
For sure. And yet, it's interesting, even back then, the authors noted that their network, despite its success, was still many orders of magnitude away from matching the human visual system.
Right. So thinking about that and seeing how much progress has been made since 2012 on recognizing static objects, what part of human vision, maybe beyond just labeling things in pictures, do you think remains the biggest hurdle for AI trained mostly like this? With supervised learning on big data sets, what's the sort of missing ingredient we might need for the next leap?
That's a great question to ponder.
Something for you to think about until our next deep dive.